Okay. Alright, so looks like we see one today. I didn't do the one yesterday because it was a previously solved one where the answer already fully loaded from earlier this year, I guess. So, yeah. But the answer that I previously solved it with was streamed and everything. Nice. Count negative numbers in a sorted matrix. Given an m by n matrix grid, which is sorted in non-increasing order, both row-wise and column-wise. Not increasing, so somewhat like decreasing. Return the number of negative numbers in the grid. Interesting. So 4, 3, 2, negative 1. So both the first column of values was decreasing, not increasing, and also the values with the rows were increasing. Huh. So clearly you can solve this using a n squared or m by n or mn algorithm, going through every single element of the grid to check if it's non-negative, or sorry, if it's negative, and then keep count of the negatives. Question is, can I do it faster? And the answer is almost assuredly. But how? Well, we could, in theory, what's the size of m and n here? Let's check, it's only 100. It's negative 100 to 100 is the values in the grid. We could use bisect to basically search for the index where you find the negative within the row, and that corresponds, and then just do some calculation to figure out how many values are after that, and then take that from the negatives remaining in the row. And do that for every row, I guess, with some modifications that look up or down like these. Sure. So let's say answer equals 0. I'll use rows and columns as the m and n variables because I like to not have just single letter variables. Rows is the length of grid. There's the number of rows. Number of columns is length of grid of 0. Length of the first row. And then I'll say for every row in grid. So row is like 1D array. Whose length is columns. So I think I'm going to use bisect to determine where to find the negative in this. So this bisect left of negative 1 is the value. So let's say index is equal to bisect left. For the array that is the row, the value is going to be negative 1, I'm going to say. Let's find the index where negative 1 occurs. Yeah. And so 0, 1, 2, it'll say 3. Length here is 4. So it should be the length minus this index should give me the number of negatives in the row. So answer plus equals the number of columns minus index. One technique to keep in mind when you're doing a lot of these calculations as to what the correct expression that you would use to identify like the number of negatives in a particular row might be. It's just to use actual values based on an example and making sure that the values that you're calculating with are correct, and then you kind of generalize what the values represent to your variables. Anyways, so that's going to work for the first row. But then for the second row, I think I can be a little more specific. Because for my second row, if it's negative here, then it would have to be, the negative would have to start. So this row versus this row, like the negative would have to be below here. Okay, anything below here is negative because of the column. This being the last column, and this being the last column, this being the biggest, or the columns themselves being non-increasing, means that this negative implies that this value is negative in the last column. So I should just search for the negative within the remaining indices. So maybe this should be some. I think it should be something like last is equal to calls, and this is going to be index here. This should be last. So this gives me actually bisect left. I want to bound the. Okay, I need to bound the high. The low is always going to be index 0. The high is going to be this last index. And then calls minus index. I think it might be last minus index. And then last is equal to index. So this changes the upper bound that I'm looking through to just be based on the upper bound that was the last index of the negatives in the previous row is how far I want to search for in the next row. I want to search anything further than that, or later than that. I think that's right. Is that right? That might be wrong, actually. The negative still, no, that's right. There still should be columns. It's just changing this last index. Changing the last index just changes where it's found, but how quickly you can search for it. But the number of items still depends on how far it is away from the columns or the upper bound. Okay. Let's go ahead and return answer and see if this works. Oh boy, oh boy. Eeks. Wow, that's really bad. Okay, let's go ahead and think about this. Why did it work? Why did it go so badly here? Searching for -1 to insert into the row. I guess I should just print out the index here. Print out index in the row. Okay. This is it's descendingly sorted, so I'm not really searching for. Well, is there a parameter for saying that this array is inversely sorted? I don't think so here. So bisect assumes that I'm doing a binary search for an increasing sorted array. Can I say that this is reverse sorted somewhere? Okay, I guess I should use AI here to help me figure out if there's a key parameter for this. For reverse sorted array. So the workaround here is using key lambda x equals -1. That's annoying. Manual implementation of binary search. That's also very annoying. I wonder how fast. I guess it's probably similar speed. Key equals lambda x -x. Alright, that's closer. Okay, so this one searched for it and found it in 3, 0, 1, 2, 3. That's correct. This one found it in 2. Interesting. 0, 1, 2, 3. Why did it say 2 here? 0, 1, 2. That's not so. 0, 1, 2, 3. I equals last. Last equals this index. 0 to 3. Row -1. I index is 3. Yeah, we're searching for I'm not sure why this is giving me 2 for this one, because I'm searching this row for -1, where I insert -1, bisect left, indices 0 to 3, and somehow it's saying it's 2, so it's asserting -1 before the 1. class equals index. And then saying 0 here. 0, 0. That seems really off. For every row, search for where you insert -1. The high is equal to the last. I mean, should this be last plus 1? Last plus 1? Can't imagine that. No, there's no way. It's out of bounds on the first go. Maybe here there should be less is equal to index plus 1. That should also go out of bounds if it's also is possible to go out of bounds. Columns minus index. Okay, let me double check here. Do, 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 do. 1, 3. Yeah, this is one. Three, 2, 1, -1. Bisect left for the row -1. Okay, let's go ahead and just do sanity check here. Let's say k equals bisect left. It's gonna be 3, 2, 1, -1. Search, insert -1. I equals 3. Why? Why is it 2? The high index that's off? No. It's really just wanting to insert it at 2. 0, 1, 2. Bisect left. Insert it at 0, insert it at 1, insert it at 2. It's just strictly wrong. Lambda x. -3, oh. Oh my lord, I see. It's because I'm reversing the lambda, so this should be I'm inserting 1 rather than inserting 1, I'm inserting 0. So I'm switching over. Okay, so if I'm switching over and considering this is -3, -4, -3, -2, +1, I want to be inserting +1 into the array. +1, +1. Yeah, it's +1. Okay, that's kind of stupid. But that's, I don't think I've made that mistake in the past, so something to add to my memory banks of things I can screw up with. Interesting. This otherwise looks okay. Okay. I don't think this was necessarily easy. Assuming that you're trying to do it the optimal way with the binary searching. But anyways, summary. Easier but slower method would be to iterate over every element of the 2D array using nested for loop over row and column indices to count the number of negative values. More optimized way is above, which relies on using binary search to identify where you would insert a negative or where you find the smallest negative, just like -1 within the sorted array, within the sorted rows, and leverage that to quickly calculate the number of negative values in the rows. More optimization can be done using the information from previous row to change the upper bound of binary search. Binary search in the later row. So there's a high parameter when you do bisect left, which is the binary search function for Python, which gives you the upper bound of the indices that you want to search through. Also, be very careful to handle searching through a decreasing the sorted array, as binary left assumes array is ascendingly sorted. So there you need to use the lambda x equals -x. Alternatively, you could reverse it by doing some sort of list comprehension to make a copy that's reverse sorted. Anyways, time complexity is going to be O of, I want to say, n log n, m log n, m log n, yeah, m log n, where the grid is an m by n matrix. Since each row needs to do, each row has length n and needs a binary search, that takes O of log n, and since there are m rows, that overall takes m times that log n. Space complexity, this just be O of 1, since no extra space is needed.